Okay, it is now my distinct honor to introduce myself to give the next presentation. Okay. Oh, thank you. Sorry. So I'm going to be talking today about the hydrology of the Scott and Shasta River watersheds and how the hydrology has responded to the irrigation curtailment regulations and the mandatory in-stream flows that has happened in the past several years. With that little box in the way, thank you. So the good news is you are the very first people to see this information from this analysis. The bad news is I'm still working on it, and I'll have some. I promise I'll have some interesting tidbits to share with you. But more insights in terms of integrating the different data sets and understanding what all means will be forthcoming when my report comes out in a few months. So, but we definitely have some interesting stuff to get started with. So we're talking about stream flow, groundwater levels, evapotranspiration, and connectivity surveys if we have time. I'm going to start with my time. So this analysis is a follow-up to a report that I finished in September of 2023 that I shared with KBMP, I think the spring 2023 meeting. And then I brought in some additional co-authors to work on a manuscript that we submitted for peer review a month or so ago. We got our comments back this week, and there's no major issues, or really no issues with the analysis itself. There's some things we need to update with the writing and the scientific context, but analysis pretty solid. And so now that analysis went through 2022. So today's presentation and the upcoming report will go through 2024. And some additional data types as well. And all three of these projects were funded by the Klamath Tribal Water Quality Consortium. So I want to thank the consortium for supporting and inspiring this work. We're talking about the Scott and Shasta River watersheds. The red stars there are the gauges at the outlet of the valleys, and the green are the agricultural yields in those valleys. In there's a time I'm going to kind of go fast on some of this stuff. Some differences, key differences between the valleys is that the Scott River, while there is surface water used, the main irrigation source is groundwater, and there's not really an effective way to control and regulate that groundwater. Compared to the Shasta, where most water is sourced from diversions from rivers and streams, there's a relatively small number of large ditches that carry the vast majority of the diversions. And there's a water master who allocates that water based on water rights. There's more of a system for regulating things in the Shasta. In the Scott, the main crop is alfalfa. Of course, there is pasture and other things as well, but alfalfa is the largest crop, and it's mostly irrigated with various different kinds of sprinklers. Whereas in the Shasta, the main crop is grass pasture irrigated with flood irrigation. And when we're looking at remote sensing of evapotranspiration, it's more difficult to tell when water is shut off on alfalfa because it's got deep roots. It can access really deep soil moisture, whereas the pasture starts to kind of die relatively quickly after it stops getting water. So in response to a petition from the Karuk tribe and a governor's drought emergency, the state water board established for the first time ever mandatory minimum in-stream flows in the Shasta and Scott. And you'll see that's the blue lines here in these graphs, for Scott River in the top row and Shasta River in the bottom row. These first went into effect in September of 2021. Irrigation season is pretty much over by that point, so it really didn't have big effects in 2021. But in 2022, the regulations were in effect for the whole year, and in the Shasta by March 15th, river flows dropped below the minimum levels, and the water master began turning off junior diversions and was able to keep river flows at and I should say, the red lines are the gauge flows from the USGS, and that dark gray is the median flow across the long-term mean. So when red is below the gray, that means it's a drier than average condition. So flows were generally met in the Shasta in 2022, except for a period in August when a large ditch turned on in public violation of the curtailment orders. But other than that, the emergency flows were generally met. In the Scott, curtailments began around July 1st in 2022, and flows quickly kept dropping and stayed below for the minimum for many months. In 2023, it was just a really relatively wet year. And so even in the Shasta River, flows didn't fall below the emergency minimums until June 29th. And so some curtailments happened at that time, but there was really only about a 1 month period where the regulations were in effect and there were curtailments. And then the regulations sunsetted on July 31st, and you'll see the Shasta there, the red line drops quickly after the regulations went away. In the Scott, I think there was really very little effect of the regulations in 2023 because the flows never got below the emergency minimums until right as the regulations were expiring, and then they weren't in effect anymore. In 2024 was another relatively wet or average year, not a major drought year. So curtailment started happening June 7th in the Shasta, and a little earlier, I couldn't find an exact date, but I think sometime around mid-July in the Scott. So the take-home message here was that the water master can regulate. There's enough flow in the Shasta that the water master can meet the in-stream mandated in-stream flows by turning off junior priority surface users. Whereas in the Scott, flows dropped below that level and remained that way for many months until it basically starts raining and the flows come back up. I'm going to go relatively quickly over this, but in the Scott River, in all of these years, there was a program of what's called local cooperative solutions, which were water conservation agreements between ranchers and the water board, where people change their practices to use less water. They were allowed to continue pumping groundwater, and that program kind of evolved over time. And we can talk more about any of these details if people want to. So to look at evapotranspiration from the agricultural fields, I used this product called OpenET. Are any of you have used this or heard of this? Raise your hand. Yeah. Okay. Yeah. It's a pretty amazing, powerful data set. It's a collaboration of many different universities, government agencies, nonprofits, and uses satellite-based data to estimate evapotranspiration for every agricultural field in the western United States. Actually, every 30-meter pixel. And it's so ET, evapotranspiration, is basically the flux of water from the surface of the land and from the plants up into the atmosphere. It's a consumptive use of water. It goes back now to 2020, and they're in the process of expanding it back to 1984, but I probably won't get to that for this analysis because it's not ready yet. And the particular way I'm accessing the data, I only have it back to 2016 right now, but if I can figure out the more difficult way to get the data for this analysis, for the report, I may be able to go back to 2000. But right now it's 2016. So here's the results for the Scott and Shasta valleys for I think it's a 7-year or 8-year time series from 2016 to 2024. These are the valley-wide amounts of these parameters. So the top line there is called reference ET in the orange. And that is how much water the crops would have consumed through ET if they had just exactly the right amount of water that they wanted. They weren't drought stressed at all. Then the red line there, the middle, that's called actual ET or ETA. And that's the satellite-derived measurement of how much water crops consume. But during the growing season, there's rain that falls and hits the fields. And so not all of that ET has to be supplied by irrigation. Any precipitation that happens during the growing season doesn't need to be irrigation. So we calculate this thing called net ET. That's the thick purple line. which is the actual ET minus the precipitation. And that's kind of a coarse proxy for how much water would have need to have been applied to the field to get the level of ET that was observed. So a few things pop out here. One is that in the Shasta River in 2022, the ET values were really low, much lower than any of the other things in the time period. And then the other was that the ET in the Scott is much more constant between years, whereas the Shasta has these big fluctuations in ET between years, more constant in the Scott. We look at the, oh, I got this out of order here. If we look at the irrigation sources, on the left there is this, the top pink line is groundwater irrigated fields in the Scott in the acre feet per year. So somewhere around 35,000 acre feet per year of ET on groundwater irrigated areas in the Scott. And it does change from year to year, but it's relatively constant. If you can compare to surface water in the Shasta, that's the green bar on top on the Shasta side, that varies a lot because surface water availability is really limited in the Scott. In wet years, I mean, in the Shasta, in wet years, there's a lot of water to go around. And in the dry years, the junior users get very little water, even without curtailments. And then you add curtailments and they get even less water. Okay, so go back. If we look at on a monthly basis, I think the only thing that I'll point out here is that red line for 2022 in the Shasta had low ET essentially across the entire growing season. It wasn't just like a few months at the end of the season that were low. It was the whole of 2022. Another thing that I got was groundwater elevation data, and I requested from Siskiyou County and Matt Parker at the county sent me this great data set that they have of groundwater surface elevations in the Scott Valley from the county, from UC Davis, from Quartz Valley, and from Department of Water Resources. It's about 7,000 measurements. Some of them are just, I think some of these sites have 5 measurements and some of them have several hundred. So it's a very variable amount of data, but if we just take the data that we have and calculate the average groundwater elevation, that's what you see there. So kind of on the fingers of the valley and the upstream side, elevations are higher. It kind of makes sense, right? Water flows downhill towards the outlet of the valley. So I took that, or another metric we can look at is the range in groundwater, right? The aquifer fills in the winter and spring, and then it drains over the summer and the fall. So here they're color coding with the dark color, the dark red is how much fluctuation there is. So sites that are really close to the river are those blues that don't fluctuate that much. It's relatively constant elevation. So I took all these individual measurements and I created it's kind of a spatio-temporal interpolation to get a continuous time series of groundwater elevations across the whole floor of the Scott Valley. It's a generalized additive model, which is similar to a multiple regression, but instead of everything being linear, you can have non-linear curved relationships between the variables. It uses things like the ground surface elevation, the distance from the river, day of the year. So, and then it incorporates some interactions between those things. So in other words, the whole groundwater surface is kind of breathing up and down from as it fills and drains over time. And it has some things like wells that are near the river are forced to not fluctuate as much as wells that are further from the river. So the purpose of the model is really to come up with a total groundwater storage for the valley. It's not really supposed to be accurate for any individual pixel, but more to characterize the groundwater system as a whole. It's important to note that I didn't use any precipitation data, snowpack data, stream flow data as an input to this model. It's purely just based on time, space, and the well level measurement. So it's kind of it's a very independent of climate in terms of how it's derived and constructed. I contacted Leland Scantleberry from UC Davis and said, hey, can you run the outputs from SWIM and show me what SWIM shows for the same thing of this one showing mean groundwater elevation. And mean groundwater elevation is an easier thing to predict, and both models look really good and really similar in that regard. So here's the map of the model predictions for the annual range in groundwater elevation. And you can see the model kind of smooths things out in space, and some things, if these match perfectly, the colors of the dots would match perfectly with the colors of the background, and they don't. But it's, I think, useful overall. So this is from the empirical model, and then Leland gave me the information for the SWIM model, and it's got much more complicated spatial patterns because they're representing, extraction of water from wells and inflows from specific tributaries. So there are some similarities between the models, but the empirical model that I developed is a lot more simplistic. What we can do then is take for every point in the model grid, we can take the lowest elevation that was predicted to occur. So in most places, this was like fall of 2015. And then we could subtract for every month in our whole time series, how much higher is water than it was during the lowest drought. And then integrate that all, summarize it across the whole valley-wide scale, say, how much more groundwater do we have at each of these time steps than we had in October 2015. And what's really cool is they match up like incredibly similar. The SWIM model and this empirical model. I ran the R squared on the correlation. I was like 0.88, which is pretty amazing because they're derived in two totally separate ways. One is based solely on the elevations, and the other is based on this really complicated simulation model. So I think it's a good sign both for the way that I summarize these data and for the performance of the SWIM groundwater model. There is a few places where they do slightly different things, where like the fall 2015 there's some kind of differences there. So I think it'd be interesting to kind of drill in and see, well, which of these models is doing better under different conditions. But overall, they're incredibly similar. Let's skip that for now. We can, well, let's see. Yeah, I'll just point out here that if you look at, you were to kind of in your mind's eye connect the bottoms of all the groundwater elevations, and in the bottom panel, the USGS flows, there's a pretty high correlation there, right, between summer low groundwater and summer low flow. So we can take the amplitude of that winter, spring filling and spring, summer draining of the groundwater, that seasonal movement, and plot that as a time series between the SWIM model and the empirical model. And they're both, they both follow pretty similar patterns. There's on average about 35,000 acre feet of change in the aquifer from the April high to the September low. And one thing that's interesting is that's almost the exact value of the ET from the groundwater irrigated fields. That reduction in the aquifer capacity over time, or over the course of the season, matches pretty closely with the amount of water that the crops on the groundwater irrigated fields transpire. So I hope in this project we do more of these water budget type comparisons. But here's one, that's one that I've got done. So I noted here a minute ago about how the low flows correspond well with the low groundwater elevations. So if we plot that correlation for 2 months here, here's August and September, it explains about 65% of the variation. And we can do some cool stuff like look at the difference between 2 years. So 2008 and 2013. 2008 had about 5 more CFS of river flow, and had about 8,000 more acre feet of storage. Or compare 2020 and 2013. where it also had about 5 more CFS and about 10,000 more acre feet of storage. So this is kind of an empirical way in which we can say, okay, if we could do some kind of project to increase the groundwater storage by 10,000 acre feet by extra recharging in winter or reduced pumping during the irrigation season, according to this model, we get about 5 CFS increase in flow. Of course, you can get similar types of numbers from the groundwater simulation model from SPIM, but I think it's pretty interesting to look at just from a purely data perspective. It's always good to look at a problem from different ways and see how similar of an answer they give you. I also developed a statistical model to predict flow from snowpack and precipitation using just the total amount of precipitation that occurred in a year and the maximum snowpack for that year. Calibrated the model with the pre-curtailment data and then applied it to the whole time series. So it sort of gives you an index of what do you, based on the snow and precip, what would you have expected the flow to be? And if we look at the Shasta River, so the x-axis here is the measured flow at the gauge. The y-axis is the modeled flow, what we would expect flow to be based on the climate. And if you look at the red dot there, that's 2022 in the Shasta, see that the model or the measured flows are much higher than what we would have expected based on climate. And that was the year where the curtailments were in effect for the entire year. So it did appear that the curtailments had this effective increase in flow. There was really no effect in 2023 here. The flows in 2023 were what we'd expect based on climate. That makes sense because it was a high flow year and the curtailments, sunsetted in the middle of the year, so there wasn't really a big effect there. We look at the Scott River, these top panels here, in almost every year and month, the flows were about what we would have expected based on climate. There wasn't like a major flow bump like we saw in Shasta. Although if you look really closely here, like this green dot for September 2024 and August 2024, the measured flows were somewhat higher, not like radically higher, but a little bit higher than would be expected based on climate. So there probably is some effect of the curtailment on flows. Let's see. I'm gonna skip these connectivity surveys. Sorry, Crystal. Very fast. Okay, never mind then. This is data that she had sent me from that are collected. Some other analyses that I'll be looking at is compliance with the LCS, with the water conservation agreements. Some of the LCSs did provide metered pumping data, so I want to compare that to the net ET from the Riverbend Sciences. And I want to look at the rebound of fall flows, like how much rain does it take to refill and get the flows back up to where salmon can migrate them. That's probably more stuff than I have time and budget for. So if anyone has any ideas on what I should prioritize, let me know. So in conclusion, there's tons of data out there. So you see a little picture here of how we can take these different data sets and combine them together to learn interesting things. And there's a ton more work to do in that regard. Another is that the streamflow results mirror the ET results. In places like the Shasta Valley in 2022, where ET was very low because a lot of the ag operations were shut off, we saw large scale increases in stream flow there. And in years and watersheds where we didn't have a decrease in ET, we didn't have an increase in stream flow. So we want to increase the stream flow at a basic scale. We have to either reduce the consumptive use or store winter water. If there is winter water that's available to be stored, without major impacts to the river. Thank you.
So in the Shasta Valley, how did you determine what crops were irrigated by surface water versus groundwater?
I didn't look at the intersection of the two crops of percentages of each and the overlap. I was kind of looking at each separately. I got some GIS data of what the crops were and what the irrigation types were, and presented the dump once for each of those, but I didn't like do an intersection. That would be interesting to do.
On one of your slides, it showed the groundwater use versus the surface water use.
Yeah, one was this or that one?
That one right there.
Yeah,
Or Shasta River.
right. So this doesn't differentiate by crop. It's just all groundwater irrigated fields.
In Shasta?
And Scott, yeah. Or sorry,
So how do you know which ones the Shasta are irrigated by groundwater versus?
that is that was a GIS layer from, I think for Shasta, I used Department of Water Resources from 2010.
Wait, Ed?
Yeah, and I have it back here. If you want to see the map,
Could you share that with me?
yes,
You might not cover it.
yes. And there's the map.
Thank you.
Yeah, other questions?
There's one online.
Yes. All right, Sean?
Thank you so much, Eli. That was a very interesting presentation. I have a couple of questions. For your snow analysis, snow streamflow analysis, what kind of snow data did you use?
Yes, I used the University of Arizona gridded snowpack data. It's essentially, they start with Prism, which is a gridded precipitation data set that combines lots of ground-based measurements of precipitation and do a GIS model on that. So the Arizona data set, snow data set, takes that and sort of does a rainfall snow simulation based on the air temperatures. They take that and then they kind of correct that based on the sporadic few snow stations that are out there, kind of stretch the fabric of the model prediction. So it's kind of a hybrid of the model and observations.
And what time did you use those? I mean, snow at what month did you use? Was it like end of April?
Yes. I just did it on the maximum annual for the year. So if that
I
happens
see.
on
Okay. Okay.
December, it could be December 15th, or it could be, April 10th,
Got it.
just whatever with the highest point on the curve.
The peak. Okay. I got it.
Yes.
My last
Yeah.
question, just wanted to be very quick. I mean, the groundwater level data that you were showing for Scott, is it the average of all the fields from the model and all the wells that you got from GSA, or like selected wells or one representative well?
Yes, the model inputs are all of these dots. So I just fed in whatever data were available and then fit this model to the available data. So it doesn't, I didn't just like filter out, say, okay, only use the 10 wells that actually, had data over the whole time period. It's just taking data from when and where it's available and hoping that these other spatial things and the time of year things help to kind of fit that into a general trend. But there definitely could be some issues with, or there were a lot of wells that started and then stopped and then started again. So it's well organized data set, but it's kind of sporadic. Any other questions?
Well, thank you, Eli.
Yeah, thanks.
First of all, thank you for taking this on. This has been such a powerful thing. And secondly, is kind of, I don't understand why, if the Shasta system is mostly a surface drawn system, why is it so much harder to model than the Scott?
It's hard to model because, it's these discrete springs and there's like lava tubes. And so, knowing how the water gets from Mount Shasta to the specific springs
I get it.
and where different wells would impact that is tricky. Yeah. To move on soon, I think. Yeah. All right. Thank you, Eli. Yeah. Probably.